Imagine a future where a single quantum computer can quietly destroy the entire Bitcoin network. No hacks, no 51% attacks, just pure physics breaking the math that holds Bitcoin together. This is the quantum fear currently doing the rounds on social media. The target? SHA-256, the cryptographic hash function that powers Bitcoin's security, mining, and addresses. But is this sci-fi fear-mongering or an actual threat? Today we're diving deep into what it would really take for quantum computing to break SHA-256, where we actually stand right now, and what's already being done to protect your coins. Stick around, the answer might surprise you. First, quick clarification. SHA-256 is not encryption. It's a hash function. You feed it any data and it spits out a fixed 256-bit fingerprint. It's one way, easy to compute forward, practically impossible to reverse. In Bitcoin, SHA-256, actually double SHA-256, is the backbone. It secures proof-of-work mining, miners race to find a hash below a target. Blockchaining, each block's hash links to the previous one. Classically, brute forcing a pre-image attack would take roughly 2 to the first 20 fix operations. That's a 1 followed by 77 zeros. The entire observable universe doesn't have enough atoms to represent that number. Enter quantum computing. Here is Grover's algorithm. Discovered in 1996, it gives a quadratic speedup for unstructured search problems. Instead of 2256 operations, Grover's reduces it to about 2128. Sounds like a huge win, right? Let's put 2128 in perspective. Even if you built a quantum computer running 10 billion operations per second, it would still take roughly 340 billion years to search half that space. No known quantum algorithm beats Grover's for cracking SHA-256. So, SHA-256's effective post-quantum security stays rock solid, even at 128 bits. Experts call this post-quantum sufficient. Now, what does this mean specifically for Bitcoin? In proof of work, a quantum miner with Grover's would get a quadratic speedup in hash searching. It might give them an edge. But it wouldn't break the network's integrity or rewrite history. The blockchain stays tamper-proof. SHA-256 is not the weak link quantum computers are coming for. But Bitcoin does have a quantum vulnerability, just not in SHA-256. The real danger is digital signatures, ECDSA and Schnorr on the SEC P256K1 curve. Schnorr's algorithm can solve the elliptic curve discrete logarithm problem in minutes. Public keys exposed in legacy addresses could let an attacker derive the related private keys and steal funds. Where are we right now in April 2026? Still in the noisy intermediate-scale quantum, NISQ era. The biggest machines have only hundreds of noisy physical qubits. Error correction is the killer bottleneck. We can create a handful of logical qubits, but we need millions of stable operations for crypto attacks. Today, zero risk. Good news, the defense already exists. NIST has standardized post-quantum cryptography algorithms, ML-Chem for key exchange and ML-DSA for signatures. These use lattice problems that neither Schnorr's nor Grover's can efficiently crack. For Bitcoin, a soft fork could introduce new address types supporting these. Bitcoin's decentralization has survived every shift before. It will surely survive quantum too. If you want your Bitcoin future-proof, keep an eye on these improvement proposals. BIPs. For more bite-sized breakdown like this, like, comment, and subscribe. Stay curious, stay secure.